It's one of the most fundamental questions a chemist can ask. How are the atoms arranged inside stuff? The answer not only tells you about the chemical structure of a material, it can reveal why it has certain electrical or magnetic properties, for example, or why it's so good at getting involved in a particular reaction. And one of the best ways to figure out that structure relies on X-rays. In this episode of Stereochemistry, we're going to take you inside the biggest and brightest source of X-rays on planet Earth, an X-ray free electron laser, and we'll hear about the amazing science that people are doing with it. But first, a little history. So just over a century ago, physicists realized that when they fired X-ray light through a crystal, those X-rays would scatter off the crystal's atoms to form a unique pattern. Not to William Lawrence brag, but the physicists had also set up a film to record that scattered light. What developed for each crystal was a unique pattern of bright spots and dark regions. That pattern is a fingerprint that tells scientists precisely how the atoms are arranged. Fast forward to the 1970s, and researchers got their hands on a new and more powerful source of X-rays called synchrotrons. These particle accelerators make electrons go so fast that they spit out bursts of X-rays. And these bursts have been used to determine the structures of tens of thousands of different proteins, for example. But synchrotron X-ray bursts are still not bright enough to get structures from nano-sized crystals, or things that simply refuse to crystallize at all. That's where X-ray free electron lasers come in. And just some record keeping up front, X-ray free electron laser is abbreviated XFEL or XFEL. XFELs work on a similar principle to synchrotrons, but they make pulses of X-rays that are a billion times brighter, so you can get chemical structures that you just wouldn't be able to see using other X-ray sources. Over the past decade, several billion-dollar XFEL facilities have been built around the world. The newest one is called the European Free Electron Laser, and it can produce the brightest X-ray pulses yet. Researchers started bringing their samples there in September of last year, but it's had its fair share of teething problems. So we sent CNN contributing editor Mark Peplow there last month to find out how it's all going. Welcome to Stereochemistry, Mark.
Hi, Matt. Glad to be here.
So what was it like going to this gargantuan X-ray facility?
It was absolutely great. You know, we often think of chemistry as something that's confined to little round-bottomed flasks in a laboratory, but I absolutely love visiting facilities where the science relies on monster machines. The sheer scale of the technology and the engineering that goes into creating these incredibly complex instruments, it's so impressive. Things like XFELs, big particle accelerators and so on, they're like science's equivalent of the Gothic cathedral.
So how do researchers actually get to use this thing?
Well, first they put in a proposal to use the X-ray beamline, and the successful ones get a chunk of time to go and analyse their samples. It could be up to 60 hours, say. At the XFEL in Japan, they'll literally work around the clock to get as much data as they can. Whereas at the XFEL in California and this new one in Europe, that time is carved into 12-hour shifts. But it's still very much a pressure situation. What makes the European XFEL a bit different from these other facilities is that right now its staff scientists are still bringing all the machinery and the instruments up to speed, even though external researchers are already bringing their precious samples in to do their experiments with the X-rays. The facility, it's still really new. It only opened to users in September last year. So there's a lot of troubleshooting going on, and it's a pretty high-stakes environment for everyone involved. I got the chance to see how that plays out when I toured the facility last month, and I talked to visiting researchers and staff about how things are going.
Well, I, for one, cannot wait to hear that. Take us to Germany, Mark.
I'm standing in a concrete tunnel about 12 metres underground, and there are two shining stainless steel pipes running at about chest height all the way along the centre of the tunnel, supported on posts. Over here, incongruously, there are a few small bicycles, and if I borrowed one I could cycle for 3.4 kilometres along the tunnel to reach DESY, the German electron synchrotron in the city of Hamburg. At the far end of the tunnel is a 1.7 kilometre long superconducting linear accelerator that boosts electrons up to very, very nearly the speed of light. Before they get here, the electrons will pass through a series of magnets called undulators to make them wiggle around and give off powerful X-ray pulses. Those X-rays fly through the stainless steel vacuum tubes and arrive just on the other side of that wall in an instrument hutch, where they will hit a microscopic sample of matter and scatter. When it's running at full tilt, it should be able to deliver 27,000 X-ray pulses per second. That's hundreds of times more pulses per second than any of the other handful of XFEL facilities around the world. More flashes means that researchers can take more snapshots of their molecules as they undergo chemical reactions or as they change shape in response to a burst of light or a magnetic field, say. And because each X-ray pulse lasts for just a few femtoseconds, a few millionths of a billionth of a second, they can capture processes that happen just as fast at the timescale where chemistry and biology and materials science actually happens. I'm going to join Alan Orville. His team are visiting the facility to put their microcrystals right in the firing line.
So I'm Alan Orville. I work at Diamond Light Source. So we're interested in determining crystal structures at atomic resolution of enzymes engaged in catalysis at room temperature. Our science drivers in this case are enzymes that degrade antibiotics. These are the so-called beta-lactamases. This is important for human health because there's many antimicrobial resistant organisms out there. That means that the enzymes have evolved an ability to degrade penicillin-based antibiotics. And we believe that if we understand the entire reaction cycle at room temperature, we'll have new insights into how we might make better antibiotics. And we do this with a serial femtosecond crystallography approach, where we have many thousands of crystals streaming through the beam. Each one interacts with the X-ray beam, explodes, then we need a new sample.
Commence primary ignition.
So wait, I know we're talking about microcrystals of enzymes, but still, they're blowing them up? How do you get a crystal structure out of something that's exploding?
Well, in the instant just before it blows up, some of the photons in the X-ray pulse diffract off the atoms in the crystal. So one pulse gives you one snapshot from one crystal. Then you spurt another crystal into the instrument, blow that one up, and get another snapshot. You keep doing that in a continuous stream until you compile tens of thousands of these diffraction experiments, all capturing the structure from different angles to build up a reliable 3D structure of the enzyme with atomic resolution.
Okay, I'm with you mostly. But how does that tell you about the enzyme's reaction cycle?
That's the clever bit. I'll let Lois Pollack from Cornell University explain it. She was at the XFEL with Alan studying these proteins, these enzymes.
So the really hard part about watching any kind of reaction as it progresses is synchronizing everything. We want to add the antibiotic, and then we want to watch how the protein interacts with the antibiotic. And in this case, we watch the antibiotic enter into a binding site on the protein. And then the goal is to actually watch the chemical reaction take place as the protein goes in and basically cuts one of the rings that's inside of the antibiotic, rendering it useless. So if you have tiny crystals, the antibiotic can diffuse in. We know how long it should take for the antibiotic to come into the crystal, and we start the clock. And at a fixed time later, the molecule flows out of our mixer into the interaction region, and then we zap it with the X-rays.
So basically what they're doing is that they're varying the delay time between when they mix the enzyme and the antibiotic together and when they bombard that sample with X-rays.
And in this way, we build up a stop motion, if you will, movie of the enzyme engaged in catalysis. But it's at atomic resolution, so we know where every atom is in that reaction cycle.
Oh, that makes sense. So that's why producing 27,000 pulses per second is so useful. It means you can gather enough data to make that movie in a lot less time.
Exactly, and that's important when there's so much competition for beam time.
But they must go through a ton of samples to get that stop-motion video.
Yeah, absolutely. The team had brought many grams of their enzyme and tens of thousands of dollars worth of antibiotics, so they really don't want to waste it.
And we talked about this earlier, how visiting scientists like Alan and Lois have only a limited amount of time to do all this. That sounds pretty stressful.
Right, and because the European XFEL is still fine-tuning all the equipment, that really ramps up the pressure. Let's go back to Alan in Hamburg.
Yeah, so they call this user-assisted commissioning, which is a unique branding, if you will.
And on the one hand, it gives the frontline scientists opportunities to really have an impact and collect unique data with their precious samples. On the other hand, they know there's a risk that the machine isn't stable and various other components are in place. So I know there are other facilities in other places that the commissioning all happens behind the curtain, if you will. Sort of like, what is it, The Wizard of Oz?
Wizard of Oz, yeah.
Here we've said, let's bring the users in. It's a different way of running things.
Now, you were having some problems yesterday getting the sample jet and the X-rays to actually coincide. It's now just gone 11 and we're 3 hours into today's shift. Have the team made any progress?
So the way this facility works is you get 12 hours of beam time. And every facility expects the first few hours of beam time to tune up the conditions.
Right.
Because the previous shift might have run the machine under slightly different conditions, and that is certainly the case here. So we're still tweaking up and cleaning up the beam so that it's so as much of the high intensity beam is focused to the region that will be at the jet, and there's less to bounce off the nozzle and various other parts that's not where the sample is.
After your shift had finished at 8 p.m. last night, you had an hour discussion meeting to break down what had worked and what hadn't. And then some of the team had to come back and do some cleanup.
That's right.
But you were also discussing potentially coming in and doing some tests before the run started as
That's right.
well.
Yeah.
I mean, those are really intense work periods.
They
day
are.
After day after day.
This is a 24-hour clock.
Yeah.
And if you have a big enough team, you often will split up into day shift and night shift activities. And if the beam is there in the night, then the day shift has to fix up whatever problems we encountered, or vice versa. The point is that you've got opportunities to recover in that 12-hour off period. And so it's very common that you get your team sort of in two different clocks.
Yeah.
And then the communication is important so that the team who's coming in overlaps a little bit with the previous shift and they know what their tasks are.
Yeah. And how do you cope? How do you prepare for that? I mean, do you sleep a lot? Or
Actually, that's, I think, the biggest risk for every facility. I mean, these are expensive hours that we're spending on the beam, and fatigue is your biggest issue, right? You can easily have a mistake with the equipment.
I see that the table is well prepared with tea and coffee, which presumably helps.
Yeah, it does. There's coffee machines everywhere throughout here, which is terrific.
And how does the dynamic work between the visiting scientists that are coming in and the instrument scientists who are permanent staff here? I mean, I can imagine if it was me and this was my baby that I'd worked on for years, and then suddenly these yahoos come in, excuse me, but you know what I mean.
Oh, I know exactly what you're saying.
Are there tensions there, or is it difficult to manage, or how does that interaction work?
So I was a beamline scientist at Brookhaven Lab before I came here, so I've seen it on both sides. I've been on the side where you're the beamline scientist, and here comes the people, and they don't even want to tell you what the sample is.
Yeah.
And I can tell you personally, that's not a great way to get people to work hard on your particular experiment. So my strategy is to include the beamline scientists early on and as deeply as possible in what we're trying to do.
So I went back to Lois Pollack to ask the big question. Did the experiments work?
Well, we're still figuring it out. I am optimistic that we were successful. One of the challenges of doing these XFEL experiments is that you generate so much data that it's fairly challenging, I would say, to be doing a real-time analysis. So you kind of have an inkling that you were able to measure something, but it takes weeks, sometimes even months, until the structures can be solved. But we do know that we acquired enough hits to be able to solve a structure, assuming that all the hits are good and that the quality is good.
So I'm curious, why did you schlep all the way over to Europe to do these experiments? The XFEL in California, the LINAC coherent light source, that's a lot closer to you.
Yeah. It's incredibly hard to get time at the LCLS. It's very, very competitive. And we've been fortunate to participate in a handful of beam times there. But since these machines have typically one experiment running at a time, the beam time is very, very hard to get. So I am just excited about any opportunity to be using our technology and really to be doing these incredible experiments. I mean, this new method of visualizing these reactions with atomic detail, it's phenomenal. And I'm so excited about the possibility that, we'll travel to Germany.
So what do you think about the decision to let users in while the instruments are still being brought up to speed, while they're still having glitches ironed out?
If the machine is in a little bit of an unknown state, then so it introduces a little more uncertainty. But I'm an experimentalist, and just doing something brand new on the cutting edge, that's kind of what I live for scientifically. So even having the opportunity to be out there when the machine is still more of a variable than eventually will be, it's an incredible opportunity for me and my group. The things that we learned in just running our injectors, interfacing with the sample people, it will all make the next experiment 10 or 100 times easier. For me, what's really neat and maybe cool about this is working with such a diverse international team of scientists. It's just kind of a wild experience. You learn a lot about the ways things are done in different places, and it makes it really interesting sociologically as well as scientifically, and that's kind of cool.
Of course, Alan and Lois were just visiting the European ExFEL. Later on, we'll hear how the staff scientists feel about opening their doors to guests while they're still getting the facility up and running.
But first, we wanted to check in with CNEN's Doria Reeser about what's new in the newsletter world.
Hey, Matt. So I know you're attending ACS Boston.
I am.
However, a lot of chemists don't get an opportunity, so we're going to bring the meeting to your inbox. And so we have this product now. It's a pop-up newsletter.
And what exactly is a pop-up newsletter?
That's a good question. I have to admit, I didn't even know what that was until I started managing our newsletters here at CNN. So a pop-up newsletter is a newsletter that you're not going to receive on a regular basis, and it usually highlights a specific topic. In this case, it's the ACS Boston meeting, and you only get the newsletter over a short period of time. In this case, you'll be getting the newsletter every day from Sunday through Thursday of the meeting. Basically, we're going to be sharing things that we saw and heard, photos, quotes, some of the latest chemistry news that's coming out. Even if you're at the meeting, you can also see what we recommend going to, some of the big sessions and highlights, as well as stuff to do outside of the meeting. So if you need an escape, you can check that out.
And do people have to sign up for said newsletter?
Yes, that is a key piece of information. So you do need to sign up for the newsletter at bit.ly/ACS Boston pop-up. Note that that's all lowercase. So it's bit.ly/ACS Boston pop-up.
So I think our next pop-up newsletter project should be, we'll get your adorable dog, Ultraviolet, her own pop-up newsletter for a week in, I don't know, maybe it shouldn't be a pop-up newsletter. Maybe it should be an all-the-time newsletter.
I think this is a really great idea.
So whether you're making the trip out to Boston and want to stay on top of things, or if you've got to sit Boston out and don't want to miss any meeting news, be sure to subscribe to CNEN's pop-up newsletter. The link again is bit.ly/ACS Boston pop-up, all lowercase. And if you're like me and you think we should have a newsletter dedicated to Doria's dog, be sure to tweet at her to let her know. She's at Dr. Doria. Now, let's get back to science's newest Gothic cathedral.
Just before we head back to Germany, let's take a look at the different instruments at the European ExFEL, the kit that allows you to prod and tweak a sample in various ways and detect the X-rays that have interacted with it. So far, there's one X-ray beamline feeding 2 instruments. Later this year, a second beamline will start to deliver X-rays to 2 more instruments, and in 2019, a third beamline will supply instruments number 5 and 6. Each instrument is set up to tackle different sorts of scientific questions about the behaviour of biomolecules, photovoltaics, magnetic materials, catalysts, superconductors, and loads more. Even with the instruments that are already online, staff scientists are still doing a huge amount of work to bring their capabilities up to full power. I spoke to Adrian Mancuso about this. He's the lead scientist for the instrument that Alan and Lois were using. That very week when I visited, the European XFEL had just doubled the rate of femtosecond X-ray pulses it produced, going from 300 pulses per second to 600, and Adrian's team had to make sure their instrument could handle it. The ultimate goal is to push that up to 27,000 pulses a second, which should happen by next year. Remember, Adrian and his colleagues are doing all of this while visiting researchers are still here. I asked him for his take on that. How does it feel when you get groups of scientists coming in for a week, just sort of turning up and using that machine that you've lovingly created and curated?
It's fantastic. Yeah. It's exactly what it's built for.
Yeah.
You have to have a certain robust ego to work in this kind of role, where a lot of what you do is helping other people do something great. But if you have that attitude, and much of my team does, then seeing the instrument used well is fantastic, because if you think really hard, what we do here is enable a whole host of science that you can't do without this. And if you realize that, you actually then realize that what you're doing is not just fun and interesting, but it's quite noble, right? So all of a sudden we're making it possible for people to investigate these sort of biostructures and systems and time-resolved systems that they couldn't see before. It's so good. And you see these people, they come and they've got their hopeful little samples and they really want to understand them. And if they go away with some data which allows them to understand that, it's fantastic. I'm very proud to say that of all of the user-assisted commissioning experiments that we've started at my instrument, we've sent them home with some data. And some of those now start to get to the phase where papers are being written up.
I put the same question to Christian Bressler. He's the lead scientist for the other instrument that's online, which has already been used to study materials found in organic light-emitting diodes and photovoltaic solar cells. How does it feel when you have random people trooping into your workplace, trying to use your baby that you worked on for so long?
The good ones don't dare to touch, and so we help them to use it. The special thing about free electron laser experiments is the fact that we babysit our external users. This doesn't happen so much at a synchrotron. At a synchrotron, it's like if you go to a go-kart place, they put you in the car, they say there's the brake and the gas pedal and the steering wheel and go. See you later. And that's how the synchrotron business works here. We have to help them through everything, even though same old beam, it's just a beam going from here to the sample, but our beam goes over a whole kilometer. And if you don't really know what you're doing, it's very easy to steer it over and it shoots somewhere and you don't know what's going on. And the beam, of course, is pretty dangerous. You can drill through thick plates of metal, no problem. So better you babysit your user.
How was the process of getting it up to speed, of actually getting it switched on and getting users in there?
It's still going, to answer that part of the question. So we're still in the process of turning on the machine, because it is a lively, complex animal, and we're learning every day about the little hiccups that it shows here and there.
Christian's instrument isn't just set up to do X-ray scattering and diffraction experiments to see where the atoms sit in a structure. It can also do X-ray spectroscopy, which reveals how the electrons in those atoms behave. Christian says this is key to developing the instrument into what he calls the ultimate molecular camera.
So it's not just looking where the atoms are and how they move, but we want to understand why they do it, and the spectroscopy tells us about the electronic changes inside the reacting molecules, and this we can then use to understand why the atoms are actually displaced as we see it in the scattering detector. So that's more or less the basic idea of it, to get the naked molecule on screen.
But some of the technology isn't quite there yet. How does it feel? Are you impatient? Or?
Of course.
Yeah.
I mean, it drives you freaking nuts if you know that you are a victim of technology development. We have high technology all over the place, which is totally fascinating. The detectors, they don't exist anywhere else on this planet. Such fast cameras to record X-rays 5 times in a millionth of a second. That's just breathtaking, fascinating. The software is pretty cool, although I could... Anyway.
Wait, what about the software?
The software. That's a sore point. Harold Zinn, head of the X-ray optics group, takes up the story.
Yes, there were a lot of initial problems, and we still have a lot of problems. So the entire software was newly developed for XFEL and barely tested before we started the user run. So the first users, they were our guinea pigs, so to say, for the software. And this is a process that is still ongoing now, half a year after we had the first users. Also on the hardware side, one has to say that there are a lot of things that are still to be learned. It is actually very amazing if you think about how good the alignment has to be in order to achieve this lasing process, which this facility relies on. So we have a section of 200-meter long magnet structures, so the so-called undulators. So you have to align the electron beam that goes through these undulators within a few micrometer. And then, of course, after some time, everything moves because the Earth is moving, and then you have to redo these calibrations to get the best performance.
Yes, you heard that correctly. The Earth beneath the European XFEL is moving.
Because we did fairly recently the construction, and we put a lot of weight of our technical equipment in these tunnels and in the buildings, we still see a lot of movement of these buildings due to the changed load. And this is actually sometimes quite large and requires us to do more frequently these realignments, and we hope that this will become better over time.
Wow. So the building and the facility is literally bedding in. It's not metaphorical, it's physically bedding into the ground.
Yes, up to 5 millimeters per year, and that is huge if you think about micrometer stability.
Yeah, wow.
That is wild. But thinking about that and this whole, what was it called? User-assisted commissioning?
Right.
You know, it sounds like they're trying to change a flat tire while the car is still moving. And our editor-in-chief was using that phrase a lot during something we just went through here at CNN. I mean, on a much less impressive scale. But we recently got a new content management system, which is software we use to help publish the magazine. Have you had to wrangle with that at all yet?
No, fortunately not. One of the joys of being a freelancer is that I very rarely have to interact with content management systems.
You know, it does a lot of good, but I do miss the days when I could just write in Microsoft Word and then, as if by magic, the production team would get my prose into the magazine. Anyway, the production team was rolling out this new software while we were publishing magazines, so similar in a sense to how the European XFEL is operating, but again, on a much less impressive scale. Of course, we ran into problems as you do whenever you do something new. And writers such as myself weren't always so happy when the system wasn't working the way we wanted it to. Now that things are working, mostly, I feel bad for the production team that had to deal with a curmudgeonly me on top of the technical problems. Where this is going is, did you get a sense of what the atmosphere is like at the European XFEL when it isn't up to snuff for the users?
You know, I did. I asked Thomas Tenscher, one of the 3 scientific directors there, about how users react when the machine simply refuses to cooperate. And he described it as intense, but he also says that's understandable.
So they're here really only for a week, and that is very intense. And then while they are here, of course, they expect a very good support and performance, which is fully justified because they all make a big effort to come here for a short amount of time. And so in this period, nothing is more important than that the experiment works, correct? Yeah. And this is sometimes very difficult to comprehend for people who say, but this was only one day in a year which did not work. But I mean, for this group, it's a one day where they are here and where the experiment happens. So you have to, basically for these people, you have always to have peak performance, because only the few days where they are here and do experiments, only these few days count for an individual user group. So we had a tough time last year to get everything running. There was also a lot of frustration that things did not run so well. Of course, for an experiment, everything has to work well. If one piece fails, everything fails, basically. So people worked really hard. And I mean, now I think we are in a more stable situation already. I mean, things run much better. And so we come to much more exploitation phase. I mean, not yet there fully, but I mean, we will get there soon, that we really can take the fruits from the trees and do experiments and publish them.
So how long do you think it will be before we start seeing publications coming from the facility and its users?
Well, when I spoke to Thomas, he reckoned that the first papers were just about to be submitted, so we could start seeing that research in the next few months.
And are there any other big milestones coming up in the world of XFELs?
Indeed there are. The XFEL facility over in California, which was the first big user facility, it came online around 2009, well, it's about to get a big upgrade. From 2020 2020, there'll be a new XFEL there that can generate up to 1 million pulses per second. That's almost a 40-fold increase on the European XFEL.
Dang. So maybe we can send you there when it opens. For now, you can read more about the European XFEL in Mark's feature article in this week's Chemical and Engineering News magazine, which you can find at bit.ly/CENEU XFEL. Now, Mark, I have one last question for you. I read your story and it's awesome, and you can see in the pictures that the European XFEL is a jungle of metal pipes and cables running everywhere. Then on top of that, you've got really intense ionizing radiation zipping around the facility. What was the safety gear like?
Yeah, it really was safety first. So special hard shoes, protective shoes, you get a hard hat, and of course they give you a radiation dosimeter to wear. Excellent. 0 sieverts. That's what I like to hear.
Huge thanks to Mark Peplow for visiting the European XFEL and recording his trip for us. If you want to check out more of his fantastic science journalism, visit www.markpeplow.com. The music you're hearing right now is Gerald's Place by Raleigh Moncrief. The music you heard at the top of the episode was Kitty in the Window, and the song you heard during our chat about the ACS Boston pop-up newsletter was The Confrontation. Both of those are by Poddington Bear. And last but certainly not least, if you're going to be in ACS Boston, I want to get on your calendar right now. Come check out Stereochemistry's very first live episode, which we'll be recording Tuesday, August 21st from 3 to 4 p.m. in the Seaport World Trade Center City View Ballroom 1. We will share more details about what we have planned for you soon, but it's going to be a ton of fun, and we would love to see you there. Thanks for listening.